we are going to look at different representations of a function and in different representations of these transformations. So the first functions we're going to compare are these three. The way that we're going to compare these best is by looking at them in their different representations. So I've got the equations here, I've got the graphs, the tables, and I've also got some verbal description. Now looking at we're going to compare f of x and g of x. Well, I want to see what is going on from f of x to g of x. Well, it looks as though it's been moved upward. Is this true? Let's look. Going up 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Each point is moved up the same distance. So the f of x is equidistant from g of x. For a rigid transformation, this distance must be preserved. We can even see that on the table. 4 to 7, the same amount has been shifted up by 3 each time. And that's how we represent it. G of x is just f of x plus 3. Let's look at f of x versus h of x. Well, it looks like it's just shifted downward. But by how much? Well, it has to be shifted down the same amount each time for it to be a translation downward. So let's look. 1, 2, 1, 2, 1, 2, 1, 2. For each point, it's shifted down the same amount. That's why we write it as h of x equals f of x minus 2 to show that it's shifted down 2. We can see this connection here, f of x plus 3 and f of x minus 2 on our equations as well. Let's look at some more. For here, I've done the same thing. For the equations, I've created the graphs and the tables and the verbal description. Let's try to make the connections between them. So looking at f of x versus g of x, what is happening here? Well, it's look like it's just moving to the left. It looks like it's shifting left 3. We have to compare, though, the distance between the points to see if it's happening the same amount each time. So here it goes 1, 2, 3, 1, 2, 3, 1, 2, 3. It seems as though for every point it is preserving the same distance. The only thing that's changing here is not the y values, though. It's the x values that are changing. So we have 4, 1, 0, 1, 4. 4, 1, 0, 1, 4. We're matching up the tables. It looks as though we are shifting 3 on the x values each time. And the way we write that is we write x plus 3 inside the parentheses. So g of x is just f of x plus 3 because this shows that we're shifting it left 3. Similarly, when we're to talk about over here, this x minus 2 inside the parentheses for h of x shows that we're shifting it to the right 2. Let's see if this makes sense. Is it shifting right 2? Well, let's look at the graph. From f of x to h of x, each point is shifted the same distance of 2 each time. You can even see that on the tables as well. 4, 1, 0, 1, 4, matching it up. Negative 2 plus 2, 0. It's just shifting each amount the same. The distance is preserved. That's going to be really important to keep in mind for the next part. Here, we really got to check that because this is different. Now, looking at our functions here, we're first going to look at f of x versus h of x. Well, it doesn't look like a shift. Something's happening here, something's different. It's not as easy to see, though, on the graph, so let's look at the tables. Well, the x values are the same. The only thing different is the y values. Well, what's changed? The only thing that has changed is the sign. So we've changed the sign on the y values, even though the values themselves are the same, which means that we've just reflected it. And I've shown that change with the sign with this negative sign right here in front of the f of x, because h of x is just negative f of x. That negative doesn't mean that we're making the values negative every time. It just means we're changing whatever the sign is. So if this was negative, it would change it to a positive. But this happens to be positive, which makes all these numbers negative. Let's compare Now, f of x versus g of x. This is where that distance becomes so important. Let's look at how the distance preserved, because it looks though it's just shifted up. But is it a translation? Well, that's where we have to look at the distance. It's gone up 1, 2, 1, 2, 1, 2. So it looks like it is, but check it out here. How much should it go up? It should go up 2, but it doesn't. It goes up 1, 2, 3, 4, 5. So distance isn't preserved. That's how we know it's not a translation. It's more of a, what we're going to call a vertical stretch. It's not a vertical shift. It's a vertical stretch. And the way we can examine that is by looking at the tables. That's why these different representations are so important to look at. Looking at my y values versus my y values here, the only difference is each value is multiplied by 2. That's why I wrote this 2 right here to show that it's 2 times the f of x values is my g of x. Now we're going to look at some different representations separately to try to figure out what is going on here. So we're going to look at f of x here in a more general fashion. So this is f of x. I've created my graph, and I also have some values from my graph right here. We're going to try to figure out what is going on. Well, with f of x, I'm going to use a different representation first. I'm going to use an equation for g of x. So g of x is negative f of negative x. That's different. It's not negative f of x, it's f of negative x. So what's that going to look like? Well, let's use a new graph, and let's use a new table. So what's going to change here? The y values, the x values, it's going to be the x values. So the x values are going to change sign. So if this is negative, it's now going to become positive, negative. It's going to become positive, positive. 0 doesn't change sign. This becomes negative, and this becomes negative. But what stays the same? The y values stay the same for our okay? So let's look for our table here. We're going to go ahead and plot these points to make our new graph. Now, this isn't going to be exact, but this is going to be the closest approximation possible. So looking at our graph, what's happened here? What has happened here physically with the shape of the graph? Well, changing this sign here, all it has done is it's flipped the graph, but it's done a reflection over the y-axis. Before we did one over the x-axis. This is different. This is over the y-axis. But you can see like how I went from one representation to the other, and I've gone and figured out the different representations here of how f of x has been transformed. Okay? So we're going to keep using f of x, but we're going to do a different transformation this time. So now, before I gave you the equation, now I'm going to give you the table for the transformation. Well, we're going to have to figure out what our equation is for h of x. We're also going to have to figure out what the graph is. Well, let's go ahead and plot the points. That seems to be the easiest method here. So let's compare here. I almost made a mistake on my graph, but mistakes are okay. Sometimes we make mistakes, we just gotta learn how to correct them. So now looking at here, the graph, we can kind of see something happening here. We can even see that in our table of values. What has changed here on our table? Well, the thing that's changed is our x values. That is what has changed here. So we can see this and call this a by how much though? How much has it shifted? Well, the distance should be preserved, so it's gone over 1, 2, 3. Which direction though? Right. 3. So what is our notation here though for the function? That is the question. What is our notation? So we've shifted it right, which means it's now f of x, right, minus 3, because we've shifted it right 3. Let's look at another one. This is our last transformation, but now instead of starting with an equation, instead of starting with a table, we're starting with the graph itself. So we want to really be able to convert between these different representations. So this is our last one, but for f of x. Let's look at the graph and see if we can kind of decipher what's going on here. Well, I'm going to go ahead and, it seems like the same values of x are being used. It hasn't shifted at all. But something's going on here. It looks as though it's changed a bit. Let's see. -5 is -1. -4 is about 0. -2 is now 1. 0 is still 0. 1 is not really quite sure yet. 3, not really quite sure exactly what that is. So we're going to kind of see what we can estimate from what we've got on our table up here and what looks like approximate on the graph. It's not a shift because distance is not preserved and it doesn't even look like it's moved at all, but some kind of change to it. Well, how can we get from these same x values to these different y values? Well, -2, -1, 2, and 1. What could we do to get these to change? So we're not adding or subtracting some kind of number, but we're multiplying by something to change the shape like this. So it looks like we're multiplying -2 by a half. -2 times a half, 1 times a half, or -2 times a half and 2 times a half is -1 and 1. So maybe if we did 0.5 times a half, we would get 0.25, which means it looks like it matches up with what we got on our graph here. And the half of 3 is 1.5, which is about right here, which matches up with our graph as well. So what we've done here is we've changed the shape of the graph, and the function itself is h of x equals 1/2 f of x, okay? So instead of doing a stretch here, what are we doing? We're doing a vertical compression. So for some instances, it was easier to go between certain representations over others. That's really why it's important to be able to go between the different representations, because one way might be easier to see or work with than another.